Good morning. How's everybody? Everybody have a fun time last night? Bad voltage was good. The EC was good. I had to go home early, so I didn't really make it to the EC. I thought I'd save my voice for this. You're welcome. My name is Jeff Gelbach. I'm going to talk a little bit about software-defined networks and the management of those. This talk is one that I've given several times before. This is just the latest refinement of it, so some of you may have seen it in the past at different conferences around the world. Let me open by, well, let me ask you a little bit about yourselves first before I talk about me. A little audience poll. How many of you would consider yourself to have done some network engineering at some point in the past? Yeah, okay, so you've configured a switch, a router, a firewall, maybe some of these things, and were you, yeah, awesome. Were you pretty disgusted by the variability between different vendors in terms of how you configure these things? Good, you should be. Okay, so let me also ask, anybody in here who has actually done any software-defined networking? Yeah, cool. Which platforms have you worked with? Okay, good. So that's Juniper's one, right? Yeah, good. Cool. So a little bit about me. I've spent a lot of time in this industry. I started, my first real network management job was for the NASA Internet Sciences Network, NASA International Sciences Network, I'm sorry, which was a pretty big IP network. That's where I really learned the basics of managing networks at scale and what's necessary to do that. From there, I jumped to a vendor called Empire Technologies, which was acquired by Concord Communications. Did anybody use their products? I know some of you did. Now they're part of CA, Computer Associates, so I was one of the lucky 8% worldwide who got some money to go away after that acquisition. I didn't want to work for CA anyway, so it worked out well. I ended up at Bell South, which was, is now part of AT&T. And we have a saying about working for the phone company in the US that they put a mold on your skull when you're hired that makes it shaped like a bell, because it was Bell Labs, Bell Communications originally. So I had my brain formed into a particular shape while I worked there. But I think I've recovered from that. And from there, there's one job in here that I left off. It was just a small, doomed telephone company. And then I jumped from there to the OpenNMS group, which is where I've been now for coming up on 8 years. So I'm now making free network management systems and consulting on them, and that's pretty great. I'm pretty much working my dream job right now. All right, so let's jump into a review of what elements constitute old school networks. We've got a few pieces here. In the old school network paradigm, we've got these things called switches, right? Their job is basically to switch layer 2 frames and to run the supporting software required to do that the way they're configured to do it. So spanning tree, probably some other stuff too. Antonio knows all about the topology things. But at base, this is what a switch does in the old school model. Typically, a switch's hardware configuration is going to have lots of physical ports. They're often configured in modules that are field replaceable. You tend to have a very high throughput data plane on these things, right? Because you're moving lots and lots of data around. And the control plane for these old school switches is driven by a local configuration. That might be one that you blew in on the CLI with iOS or with Junos, or that you configured by a terrible web UI with another vendor. But yeah, it was a locally stored configuration, right? Pretty scary to think about when you've got thousands of these things. You'll notice here I'm using some terms that may not be familiar to some of you: data plane and control plane. So the data plane is just the part of the switch that's concerned with keeping the data moving. It's the backplane, the fabric, the ports, and the control plane is the part of the switch that's concerned with everything else, making decisions about which frames go in and out which interfaces. And with what policies. So these are terms that I'll pick up more on later. All right, other functions of, another component of our old school network paradigm is the router. Everybody knows what they are. They operate more or less at layer 3. switching, forwarding IP packets. They also run routing protocols. They have a more complex job. They're making decisions at a higher level. And sometimes they do stuff above layer 4 too, but for the most part, we'll say routers in the old way are concerned with the network layer, layer 3, IP or what have you. Compared to switches, routers are typically fewer physical ports. Usually they're more expensive technologies. You've got fewer of them. They're often modular, like switches. And the data plane's throughput is probably less than your switches, but often still quite good. But again here, the control plane of your routers in the old school model, driven by a local configuration. You should be getting angry. Are you angry yet? You should be. It's terrible. Firewalls also, we'll talk a little bit about firewalls. Their job basically, again, is to forward or not forward layer 3 packets, network layer thingies, IP, subject to some rules to try to keep your network safe. And of course, their other job is to take the blame when anything doesn't work correctly in the network, right? That's where we all point the finger. It's the firewall. Compared even to routers, relatively few physical ports typically on a firewall device, and a low to medium throughput data plane. Guess where it's configured? Control plane, locally configured almost always still. So even if you're using something like one of the big vendors that has a platform for keeping your rules, you still have to push them to the device. They're still stored on the device, and you still have to be concerned about whether or not the right config is running on the right device. So to help out with some of this, we've invented things like inventory and configuration management, things like Rancid or Cisco, what was it called? Cisco Works LMS, LAN management solution. This whole breed of software products, both free and proprietary, whose job is to make sure that the right configurations are running on the right devices at the right times. Also, another job that these things tend to have or get forced into is to account for your hardware elements in your network, making sure that all the ones you expect to be there are there and that ones you don't expect are not present. They're also great at eating your time and your money. If you need to blow some budget, configuration management is a good way to do it. So these things are addressing really two separate problems here. The loading of configuration onto the right devices and accounting for your hardware elements. These are really two separate concerns. Each one of them is pretty hard, so nobody's super good at this, really. There are a few, but they're very, very expensive proprietary products that do almost everything right. Typically, though, even these best-of-breed configuration management platforms don't really understand the configurations in context. They're just pushing around versions of text files or XML documents or what have you. So they don't know what's happening in the control plane. There's no awareness in your configuration management system of what it means when you turn on OSPF or when you turn off ISIS. They don't know what that means to the working of your network. And also, typically, unless you have a high-touch manual component to it, your configuration management platform can never tell you for sure whether all the nodes that are in your network are actually in your inventory. You can have rogue switches and routers out there that are not attached to your configuration management system that are actually sometimes a critical part of your network if you're not very careful with your change control procedures. Okay, so all of that. Now, where does this touch on OpenNMS? Your network management system is closely related in some ways to your configuration management system. In fact, it's so closely related that it's only they're next door neighbors in the FCAPS model. Everybody here knows FCAPS? Fault management, configuration management, accounting management, performance, and security management. OpenNMS adheres roughly to this model. Other models are available. This is the one that the OSI created way, way back in the murky mists of time. We adhere roughly to it. Another popular one is the ETOM from the ITIL guys. But our focus with OpenNMS is on fault management and performance management. We're not so good at configuration management. We have basically no capabilities around accounting and a little bit around security. So we tend to be complementary with configuration management platforms. This is going to be very basic. I apologize. This is a repurposed talk. For those of you who already have OpenNMS knowledge, this will be a review. Our 4 big concerns are: how do we get everything provisioned into the system? How do we make sure that the things are working and responsive that are in the system once we've provisioned them? How can we tell if a network element is having a problem once it's provisioned into the system? And for performance management, how can we quantify time series metrics, like how full is that file system, or how many users are logged in, or how many bytes have transited a given network interface? These are the 4 things: provisioning, service assurance, fault management, and performance management that OpenNMS is generally concerned with. And this fits together with configuration management bits that we talked about before. So one of the tools that we've classically used since the 1990s for doing these jobs is SNMP, the Simple Network Management Protocol. How many of you know about SNMP? Yeah, everybody. And everybody in this room, this is atypical because I've given this talk at conferences where a lot of hands went up when I said, how many of you use SNMP for sending email? Yay, no hands went up, I love that. So in bigger rooms at bigger conferences, I tend to get at least a handful of people who think that I'm talking about the Simple Mail Transport Protocol when I say SNMP. Good, I'm glad. I love being in a room where nobody makes that mistake. Yeah, so SNMP, functionally, really there's 2 modes of communications. There's the manager to device mode of communication, where we ask the device for some piece of information and it answers us. And then there's the managed element to manager unsolicited messages communications channel, or traps, or also informs. And these are the 2 functions of SNMP. We can talk to all kinds of devices over SNMP. Routers and switches really are where the big action is with SNMP, although you'll find it on servers as well. But yeah, the action that we're most interested in when we're talking about networks is on the routers and the switches. We talk to the SNMP agent on the managed node, and we gather data like interface traffic, BGP statistics, environmentals, anything else you can imagine. Some of you have configured custom SNMP data collection and know exactly what I'm talking about. Others will have to use your imagination a bit. But SNMP is infinitely extensible, asterisk, by this management information base, or MIB, notion that it has. So it's designed to be extended by standards bodies and by vendors and by people running clever examples in training classes. All right, so let's summarize just a little bit before we jump into the future. Old school networks, you've got a lot of nodes making their own decisions using local configurations to drive their control planes. They're switching decisions, their routing decisions, their dropping or sending a fake TCP reset if they're a firewall kind of decisions. When we're lucky in this old world, traffic does basically what we wanted, right? But it's impossible to simulate. I mean, you can try. Vendors do exist who do network simulation, but it's never really possible to give an accurate simulation of what a large-scale network is going to do when you put a certain traffic load on it. Clearly, this was not designed by hackers, right? No hacker would design a network this way. So let's talk a little bit about software-defined networks. And pardon me for 1 second. All right. If you take away just one fact from this talk, it is this. Software-defined networks as a concept is about separating the control plane from the data plane intentionally and making it programmable. Got it? Anybody not have this nugget already? Everybody's pretty well got this concept already under control? Okay, good. So we flatten the terminology a bit when we're talking about software-defined networks. Whether it's a router, a switch, a firewall, no matter what layer the device is designed to be working at, we just call it a switch. The function of a switch is to move frames or packets just to make decisions, the same kinds of decisions that those other devices were making that tended to be special purpose. The rules for making those decisions, the configuration that runs on the control plane, in this new world come from a controller. an SDN controller. The switches themselves tend to be comparatively generic hardware. Sometimes they're just commodity PCs with a lot of interfaces in them. Everything nowadays is a Linux box, right? At the end of the day. Sometimes they're virtualized even, and you're using VLANs to move traffic around inside a virtualization platform, your vCenters or your EC2 kind of things, yeah. And again, regardless of what role they're actually occupying, regardless of whether they're mostly concerned with switching or routing or firewalling, we call it a switch. That's the device. Good, okay, so that brings us to the control plane. Control plane's job is to control the behavior of the switches. So the control plane controls the data plane, good. According to centrally managed rules, which makes the configuration much, much easier. You're making all of the configurations in a central location, they're stored on the controller, and the devices get their configuration from the controller. So your configuration management system just got a whole lot easier to implement. Also, all the nodes in a controller-based software-defined network have to register with a controller. So you know about every device that's in your network if it's registered to your controller. You can't not know about it unless the controller is lying. I don't know if Volkswagen is making an SDN controller yet or not. Sorry, couldn't resist. The controller also exposes the inventory and configurations via a theoretically open set of APIs and provides scripting hooks for network programmability. Often the hooks are written in Python, which, interesting choice, but widely known language and not a terrible one. The controller is just a general purpose computer. It's probably a PC running Linux most of the time. It might be running FreeBSD or something else. It's up to the vendor. The controller might have vendor branding on it. Cisco makes controller, Juniper makes a controller, others make controllers, but there are switch vendors that have no controller agenda. Anybody familiar with Arista Networks? They make super high-speed Ethernet switches that can talk to anybody's SDN controller. They don't have a horse in the race when it comes to making a controller. They say, tell us whose controller to use and we'll use it. Or you can run it in a controllerless mode and it'll be an old school Ethernet switch. Like the switches, the controller may be virtual. I'd say the chances of the controller being virtual are actually much greater than the chances of the switches being virtualized. So in summary, we've got a bunch of relatively dumb hardware devices, switches, following rules, registering themselves to a controller so that their inventory and configurations can be managed centrally. We have programmability for the network now, which is pretty cool stuff. We can actually write code to decide what happens in our networks. Yeah, you can do awesome, wacky things. You can do agile things. You can reconfigure your network on the fly pretty effectively in this world. So now, more than, remember with the old school, it was kind of if you were pretty good at your job and you got lucky, the traffic did what you asked it to do, what you intended. Now it's mainly about skill, right? The main thing you have to get right is to be good at your job of configuring the network. It might even be unit testable, guys. How many people get excited about that? We could write unit tests for our freaking networks. Yes, I love it. This is how hackers would build a network, right? Yeah? Can I get an amen? That doesn't work here, okay. So I did a little case study. This is a little bit dated. This was one I did back in February, and things have probably changed a little bit since then. But I wanted to get a look at an actual example of a switch and a controller and see what this stuff is all about, since it's still pretty early days, right? There aren't a lot of vendors that have firmly planted a flag in this space yet. It's firming up day by day. But at the time, and probably still, the most advanced and functional open source OpenFlow controller, OpenFlow being one of several competing standards for software-defined networking, was Apache licensed Project Floodlight, which is maintained by Big Switch Networks. I believe it's considered an Apache project. Maybe it's an incubator project right now. You can get this yourself, run it, build it from source. I did from projectfloodlight.org. It's pretty easy to get going. It's a Maven-based build, big code base, Java code, so not unlike building OpenNMS. Pretty comfortable for me. The switches that I used in my little proof of concept were just Fedora 21, actually EC2 instances. Why not? They're cheap. Running OpenVSwitch, which is an SDN switch platform that speaks OpenFlow and actually runs as part of the Linux kernel. There's a userland component, but most of it's actually implemented in the kernel. Just like Project Floodlight, it does implement OpenFlow 1.3, so it can talk to Floodlight. It's also Apache licensed. And the maintainership of OpenVSwitch is distributed. So there's a kernel space implementation in both Linux and FreeBSD. So you're likely to find switches running OpenVSwitch on both of those platforms. And NetBSD also has an implementation, but at the time that I was doing this research, at least, it was a pure userland implementation. So probably slightly less performant, but of course it's NetBSD, so you can run it on literally anything, including your toaster or your espresso machine. OpenVSwitch.org is the website for the OpenVSwitch project. If you want to play with this yourself, go do it. But you'll typically find everything. I found everything except a couple of utilities came in the box on a basic Fedora 21 installation. So you don't need to install a lot of software to get OpenVSwitch running. So conceptually, what can we do with a combination of OpenVSwitch and Project Floodlight for provisioning and inventory purposes in OpenNMS? That was one question I wanted to answer here. Really, there are two options. One is to push the inventory from the controller, from Floodlight in this case, to the OpenNMS API. And this approach leans on the SDN controller's internal programmability, because probably you're going to need to make some slight changes to tell a particular node manager about your inventory. Option two was to pull the inventory from the controller's APIs, which leans on the SDN controller's API, of course, so that needs to be good and robust and something that gives us all the data we need. So let's look at each of these in turn. Push mode, conceptually pretty simple. In the case of Floodlight, they have a pluggable notification manager infrastructure. So much like OpenNMS, Floodlight is designed as a platform that a vendor could take and build a more advanced thing on top of that has a more fixed set of capabilities. So a lot of their code is made up of Java interfaces. And you can tell that they used to be C++ programmers because they start all their interfaces with the letter I. Why that's necessary, I don't know, but you can spot a C++ programmer a kilometer away by looking for that. This is an interface for a notification manager. It just takes a string. This post notification method just takes a string and does something with it. The default implementation for a notification switch listener, which implements this, it's actually a sub-interface of this interface. It just takes in a switch ID and it posts a notification saying switch and then the switch ID connected to the controller. So this is pretty dumb and fairly useless for our purposes. The default implementation just squawks a message and it ends up in your syslog. That's where it ends up going at the end of the day. We could write a new one that instead of doing a syslog message would do an HTTP post to the OpenNMS requisitions REST service. That would work to add a node every time one was added. Don't know whether they implement one that tells us when a node goes away though, so don't know what would happen there. Or we could just watch the logs from outside and do the post from an external script that's watching the logs all the time. That's the quick and dirty way to do this in push mode. Overall, both of those approaches seem a little bit dirty to me, so I thought probably this is not the best way, but it's probably effective, right? We could probably make this work. If there's anybody in here who's hacked on Floodlight or another SDN controller and has comments on this approach and its viability, I'd love to hear them either now or after. Yep, so we'll move on. Option two, pull mode, talking to the controller as a source of truth. we can query Floodlight's core controller and switches REST endpoint. So one of the cool things about Floodlight and about OpenFlow in general is pretty much everything's a REST API. Pretty modern, pretty slick, pretty easy to work with. I set up these this switch and these two switches in this controller. If anybody can spot my host naming convention here, you get a bonus. So we talked to the controller, who's Mal, and we asked for core controller switches in JSON format. So it tells us about this switch. He has an IP address of 10.0.0.138, and his OpenFlow control port is 45261. This is when he was connected for the first, or in his current incarnation, this is when he connected, and that's just milliseconds since the epoch. And switch DPID. DPID is data path ID, and this is, as far as I can tell, always going to be a MAC address. Technologies that are not Ethernet-like, probably you'll have different data path identifiers, but most of what we're doing these days is all Ethernet anyway, so consider that to be just a MAC address. And we've got the second switch, who's at a different IP address, and OpenFlow control is on a different UDP port, has been connected since, around the same time, and has a different switch data path ID. We can also get the details, so here we get an overview, right? We don't get enough information about each switch to know much about it, but we do have its IP address and data path identifier, which looks like pretty good information to put in a requisition to me. We can also dive into each individual switch and get some more information on the individual switch. So the switch's description here, version OF13, this is OpenFlow version 1.3. Manufacturer description, I don't know, does anybody know who Nicira is? I guess it was the company, maybe they don't exist anymore, that started the Open vSwitch project. I've been meaning to hook up like an Arista switch to a Floodlight controller and see if more interesting stuff comes out of here. Hardware description, Open vSwitch, not very descriptive, but again, presumably proper vendors would fill this in a little bit better. Software description, I guess this is the version of the Open vSwitch code base that's running on it. It would be different for different vendors. This would be like an iOS or an XOS rev for a Cisco device, for instance. No serial number. Yeah, that makes sense. This is commodity Intel hardware, so serial numbers aren't really a thing there. And there's no description for this device's data path. Don't know where to configure that. Never did figure it out with Open vSwitch, but I'm sure it's doable. So we can get, we're a little bit short on details, but again, that's just on Open vSwitch. I haven't had a chance yet to play with other vendors' OpenFlow supporting kit and see if it gives me better information. If anybody of you has played with other vendors' stuff and knows that it gives us better information, or if it's about this crappy, love to hear about it, either now or after. You can also query to get the endpoints for the paths for the ports on these switches. You can query the core switch DPID, which is that data path identifier, right? Data path identifier being this guy, so essentially a MAC address. So you plug that in here and /port desk. And that's going to tell you about all the ports on that switch. So you can get information about the individual ports. Again, this is OpenFlow 1.3, and then we got a list of port descriptions. This is just JSON again. So port number 1 has this hardware address. It's called ETH1. It's in a configured state. It's in state of 1. I don't remember why I have this ellipsis here now. Current speed, what is that? 100 megabit? I can't count zeros. I think that's 100 megabit, and max speed looks like it's gigabit. Port number local. This seems to be the interface that the controller is listening on. I'm sorry, that the switch is talking to the controller on, best I can tell. We have a hardware address for it. We've got a name for it. In this case, it's bridge interface. I think this is just to say that I left some other items out of the output, but you can get information about the individual ports via this REST endpoint. So yeah, we could build a requisition or a PRIS source plugin based on this data, using the data path identifier of each switch as its foreign ID in the requisition, and it would look something like this. So model import, we have a foreign source name. Here we've got a node with a foreign ID taken from the data path ID. We have the node label, which we got, I'm not sure exactly how we got that. That's a gap at the moment, how to find the node name. Maybe DNS reverse resolution would be a good way to do that. I'm not sure yet. We have the IP interfaces. Those all came out of the REST API, and we can assume that one of them is the SNMP primary. Maybe we just go with the first one. Maybe we just seed it with one interface, which is a nice pattern anyway to do for requisitioning anyway, and let the node scan take care of finding the rest of the layer 2 interfaces and layer 3s. Yep, another node, different foreign ID, also from the data path ID, different IP address, also has an SNMP primary interface. Done. So now we've got an inventory of switches by asking the controller for its inventory. So this makes sense to everybody? Anybody got a big mental gap there? You know what a requisition is and everything's filled in? Good. Cool. Okay, so that was inventory and provisioning. Service assurance, how can we take care of that? I did less digging on this, but the controller does expose whether a switch is there or not. So we can get a node up, node down kind of notion by asking the controller, hey, where's the switch that is in my inventory? And again, since we're asking the switch for its, we're asking the controller for its switch inventory. If a switch goes away from the controller, it'll also go away from our requisition, and that takes care of that inventory problem right away. Most things other than the presence and absence of switches are probably better done through synthetic transactions like pinging the switch directly. That still is a thing, right? Even in a software-defined network future, we can still ping stuff. And nothing succeeds like ping when the network's actually working. Seems probably there's not going to be a lot of change in this area, not a lot of disruption brought on by SDN and NFV. Fault management. The controller is able to send unsolicited messages, not necessarily in the form of traps, but similar in function. OpenFlow has this notion of unsolicited messages, and they look something like these. Switch, and then a switch data path ID joined the controller, and switch some other one left without saying goodbye. These are not a well-developed thing yet in the Floodlight code base. They may be better developed now than they were when I was playing with this back in February. And also, since Floodlight is designed to be a platform for other vendors to build on top of, that seems to be their business model, downstream OEMs may be providing better notification managers. Of course, OpenNMS has all the frameworks in place to reparent data from these unsolicited messages onto the correct node. We can just use the event translator for that to do a lookup and find the node based on the data path ID in a message like this. Performance management Floodlight exposes interface level metrics as well as some other things via its REST APIs. I didn't show any of this, but it's just numbers in JSON. So you can get things like equivalent information to what's in the basic SNMP interface counters. We can collect performance data directly via REST using the XML collector. How many people knew that already? That the XML collector in OpenNMS can also be a JSON collector? Yeah, you just got to switch the handler class that it uses, and it will just collect JSON. You just configure it the same way with XPath that you would for XML, and it natively eats JSON. It's really cool. So no code required for that. Data is trivially reparented onto the other node because the XML collector is also extremely flexible in deciding where the data lands that it's collecting. Oh, hey, yeah, I did actually put some port stats in here. So port number, received, transmit, bytes received and transmitted, drops in each direction, receive and transmit errors, frame errors, overrun errors, CRCs, collisions. So the same basic kinds of things that are in the if table and the fx table. These are all right here. The only thing I don't see in here is the port name. So we'd have to do a little bit of finagling potentially to get the port name out of this. But there's a but. There's always a but. The scalability of the REST and JSON-based data collection notion to really, really big levels is kind of unproven. When we talk about collecting huge amounts of data, I'm skeptical that anything that rides over TCP is going to scale, at least in a pull-driven model. So probably it's going to be fine, at least in first world kinds of networks, but in third world kinds of networks, maybe not so great. We may see a breakdown when we try to do REST over HTTP for really large scale data collection. Have to see what comes with the future. Most of your SDN switches that are on the market, at least today, they also support SNMP, and everybody's network management system knows about SNMP already, so we might as well use that. I predict, this is my prediction, feel free to put money on it, bet against me if you want. We'll have a gradual transition away from SNMP to a controller's API for data collection. It's probably going to be a slow start, and people will bump up against limitations and figure out ways around them. Consistency across different controllers' APIs is going to be key to driving this change away from SNMP and into controller-based data collection. And probably we'll end up doing things like MQs and those sorts of things to move the data around without having to do so much poll-driven talking. So a few conclusions. Still early days. I think that is still true even now, even some months after I originally gave this talk. Things are firming up a little bit, but the landscape is still changing pretty frequently. You know, we had this big debacle with Cisco being all in for OpenFlow. The future is going to be OpenFlow, and it's going to be open, and it's going to be programmable. And then Cisco kind of thought, oh wait, how are we going to make money in that future? And kind of took a step back from OpenFlow being ALICE. Most deployments that we at the OpenNMS group see in our customer environments are hybrids. There's some old school stuff and some SDN stuff laid on top of it. Most of the customers I've seen using Arista switches, which is just a vendor I mentioned before, are using them controllerless. So they'll potentially have a transition path as long as they stick with Arista. And they seem to be a good vendor. So if you're looking for fast Ethernet switches, they don't pay me to say this, but take a look at Arista. They're competent, they know what they're doing, and their product is performant. We've had some practice also with similar movements to things like virtualization. You know, virtualization has changed things a lot, but it hasn't fundamentally changed, right? We're still talking about servers and nodes and things. So it'll be, the future will look a lot like the present, just different. And if you're a person who works on SDN full-time or thinks about SDN part-time or just likes to drink beer, let's have a beer. There's some beer downstairs, so I'd love to do that. Okay, and my hook line was, of course, is SNMP really dead this time? Right, pundits have been predicting the death of SNMP since about 1989, I think, when it was first really standardized. It'll never work, it'll never catch on. Oh, we've invented something better. If I had $1 for every time a vendor invented something better than SNMP that was dead within 2 years, I'd be a very rich man. Yes, SNMP has problems. It's painful as hell to implement. Lots of crap SNMP agent implementations do exist in the world, and I have to deal with them on a daily basis. Ken has to deal with them on a daily basis. Some of you do too, and you know the pain that is dealing with those. SNMP's structure of management information, the SMI, can really struggle to model the complex kinds of relationships that today's networks involve. So that's definitely a challenge, and that's a hard nut to crack without fundamentally reforming SNMP. The stateless nature of SNMP is increasingly problematic with larger data sets, right? Because when you do a get from an SNMP agent, the data might change while it's being returned to you from the agent. That can be problematic. There's no such thing as the notion of locking a table while we retrieve it. You just use a get bulk or a get next to get the whole table, and it might change out from under you. But SNMP is still useful. It's still really useful, guys. Everybody here uses SNMP still? Everybody hates it? Everybody also loves it? Yeah, okay, that's how it is with SNMP. It's entrenched and it's useful, and that adds up to a durable protocol that's going to be around for a little while. So let's not let's not ring the bells for SNMP just yet. Questions? I'd love to hear them, either here or shoot me an email. I'm always on Freenode. I'm away a lot lately, especially when I'm traveling, but I'm there. I'm Jeff G. I'm always on #OpenNMS, and I'm jeffg.org, all spelled out on Twitter. So questions here and now. I think we're out of time, but I think we got started late, so these guys look pretty chill. Cool. All right. Any questions or conversation? Come on. Come on. I didn't bring a freaking 500 € tablet to give away, but somebody asked me a question. Nothing? Okay. Well, thanks very much for your attention, and yeah, let's chat later.